the universe's hidden majority. Most of the cosmic structures we observe represent only the visible tip of a vast hidden reality that governs the universe's behavior and evolution. We can observe only 5% of everything that exists in the universe through telescopes and other instruments. The remaining 95% consists of dark matter and dark energy, mysterious components that interact with regular matter only through gravitational forces. Precision measurements from the Planck satellite have determined the universe's composition with unprecedented accuracy. Normal matter, which forms stars, planets, and everything we see, accounts for just 4.9% of the universe's total energy content. Dark matter comprises 26.8%, while dark energy makes up 68.3% of cosmic energy density. These percentages come from the most precise cosmic microwave background radiation measurements ever achieved, with uncertainties smaller than 1%. The South Pole Telescope's SPT-3G survey has provided independent confirmation of these proportions through observations covering approximately 1/25 of the sky, with sensitivity exceeding all previous measurements taken from space or ground-based observatories. Gravitational effects provide the strongest evidence for dark matter's existence through observations of galaxy rotation curves and gravitational lensing phenomena. Spiral galaxies rotate too fast for their visible matter alone to hold them together, requiring additional invisible mass to prevent stars from flying apart. The galaxy rotation problem appears in thousands of galaxies where stars at the outer edges move at speeds that should tear the galaxy apart without dark matter's gravitational influence. Galaxy clusters show similar effects, with member galaxies moving too fast to remain bound by the gravity of visible matter alone. The bullet cluster collision demonstrates dark matter's presence by showing how gravitational effects separate from normal matter during the collision between two massive galaxy clusters. X-ray observations reveal hot gas from normal matter, while gravitational lensing maps show where the invisible mass actually resides. The clear separation between these components provides some of the strongest evidence for dark matter's existence as a distinct physical substance rather than a modification of gravitational physics. Dark energy drives the universe's accelerating expansion by exerting negative pressure that creates repulsive gravitational effects throughout space. Type Ia supernovae observations in distant galaxies reveal that cosmic expansion has been accelerating for the past 5 billion years rather than slowing down as expected from matter's gravitational pull. These supernova explosions serve as standard candles because they all release the same amount of energy, allowing astronomers to measure distances to galaxies billions of light years away. The James Webb Space Telescope has refined distance measurements to nearby galaxies, helping resolve discrepancies between different methods of measuring cosmic expansion rates. Professor Wendy Friedman's latest calculations using both Webb and Hubble data find a Hubble constant value of 70.4 kilometers per second per megaparsec, plus or minus 3%. This result brings the supernovae measurements into statistical agreement with cosmic microwave background data, confirming that the standard lambda CDM cosmological model accurately describes the universe's expansion. Recent observations have constrained dark matter and dark energy properties through measurements of cosmic microwave background radiation patterns. The cosmic microwave background reveals how dark matter influenced structure formation during the first 380,000 years after the Big Bang. Temperature fluctuations in this ancient light show the imprint of dark matter density variations that eventually grew into the cosmic web of galaxies and galaxy clusters. These measurements provide independent confirmation of the lambda CDM cosmological model while testing alternative theories about dark energy's behavior over cosmic time. The DESI survey measurements indicate a preference for evolving dark energy rather than Einstein's cosmological constant, though these results remain within statistical uncertainties of the standard model. The survey measures baryon acoustic oscillations and galaxy clustering patterns, providing another independent check on cosmic composition. However, the standard lambda CDM model remains the most consistent with current data from multiple independent sources. Computer simulations of dark matter structure formation now reproduce observational data with remarkable accuracy by modeling the gravitational interactions of billions of dark matter particles over cosmic time. These simulations show how dark matter forms a cosmic web of filaments and nodes where galaxies eventually form through gas cooling and star formation processes. The results confirm that dark matter provides the gravitational scaffolding necessary for cosmic structure formation while revealing how galaxies acquire their observed properties. Future missions will attempt to identify dark matter and dark energy through multiple complementary approaches, including precision cosmological measurements. The Nancy Grace Roman Space Telescope will measure cosmic expansion through observations of Type Ia supernovae and gravitational lensing effects across billions of galaxies. The Euclid mission will map dark matter distributions through weak gravitational lensing that slightly distorts background galaxy shapes. Ground-based telescopes like the Vera Rubin Observatory will discover thousands of supernovae and measure baryon acoustic oscillations and galaxy clustering patterns. These missions will test whether dark energy properties remain constant over cosmic time or evolve in ways that might reveal its fundamental nature. The measurements will provide independent expansion measurements that cross-check results from different observational techniques. The Euclid mission is specifically designed to map the geometry of the dark universe and constrain the equation of state parameter for dark energy. The humbling reality emerges that 95% of the universe consists of components whose fundamental nature remains largely unknown despite decades of intensive research. Scientists can measure dark matter and dark energy's effects on cosmic evolution with exquisite precision while understanding only their gravitational influences. This situation represents one of the most profound mysteries in science, where the vast majority of existence operates through mechanisms that remain hidden from direct observation. Yet these invisible components have shaped every structure we observe, from the smallest galaxies to the largest cosmic web filaments, creating the framework within which all visible matter organizes itself across the observable universe. The boundaries of what we can directly observe, however, may represent only the beginning of an even more extraordinary cosmic reality. Beyond the observable universe, theoretical frontiers. Theoretical physics suggests that reality extends far beyond what our telescopes can reveal, pushing the boundaries of scientific inquiry into realms that may forever remain beyond direct observation. Our cosmic horizon marks the boundary of everything we can possibly observe, extending 46.5 billion light-years in all directions and encompassing everything from which light has had time to reach Earth since the Big Bang. This boundary exists not because space ends there, but because we cannot receive information from regions farther away due to the finite age of the universe and the speed of light. The concept of what lies beyond the observable universe remains one of the most captivating topics in modern cosmology, challenging our fundamental understanding of cosmic boundaries and the very nature of reality. Scientists explore the limits of current knowledge through theoretical frameworks that attempt to describe what might exist in regions forever hidden from our view. These investigations force us to consider whether our universe represents the entirety of existence or merely one component of something vastly larger. Inflation theory provides a scientific foundation for considering regions beyond our observable universe by describing how rapid cosmic expansion in the early universe could generate multiple distinct areas of space. The inflationary epoch lasted from 10 to the power of negative 36 to 10 to the power of negative 32 seconds after the Big Bang, during which space expanded faster than the speed of light by factors exceeding 10 to the power of 26. This expansion stretched quantum fluctuations to cosmic scales, creating the density variations that eventually became galaxies and galaxy clusters. Some theoretical models suggest that inflation never completely stops throughout all of space, continuously creating new regions that undergo their own expansion events. Each expanding region could become a separate cosmic domain with its own space, time, and potentially different physical constants. This process might resemble the formation of bubbles, with each bubble representing an independent cosmic region within a larger structure that extends beyond our observational capabilities. Current scientific thinking addresses whether the universe is finite or infinite through observations of cosmic geometry and theoretical considerations about spatial topology. Measurements of cosmic microwave background anisotropies indicate that space has flat geometry within observational uncertainties of 0.4%, suggesting that the universe could extend infinitely beyond our observable horizon. If space is truly infinite, then the implications become profound for understanding the total scope of cosmic reality. The mathematical frameworks developed to describe these scenarios draw from string theory and quantum field theory, which naturally produce predictions about regions beyond our direct observation. String theory allows for different configurations of extraspatial dimensions, each potentially creating cosmic domains with distinct physical properties. These mathematical structures provide specific frameworks for understanding how different cosmic regions might exist and what their properties could be. Evidence from cosmic microwave background radiation patterns reveals subtle anomalies that standard cosmological models struggle to explain completely. The Wilkinson Microwave Anisotropy Probe and Planck satellite detected unexpected features in the cosmic microwave background, including temperature asymmetries between different hemispheres of the sky. The South Pole Telescope's latest observations have refined measurements of these anomalies, though scientists continue investigating whether they represent signatures of physics beyond our current understanding. Quantum mechanics introduces additional theoretical possibilities through interpretations that suggest reality might branch into multiple parallel versions. The many-worlds interpretation proposes that every quantum measurement could split the universe into separate realities corresponding to all possible measurement outcomes. This process would create an exponentially growing number of parallel cosmic domains, with each branch containing observers who experience only one outcome of each quantum event. The philosophical implications of these theoretical frontiers challenge fundamental concepts about reality, identity, and the uniqueness of human existence within cosmic evolution. If regions beyond our observation contain variations of cosmic evolution, then questions arise about the nature of physical loss, the meaning of individual existence, and our place within the broader cosmic context. The anthropic principle gains significance in these scenarios, suggesting that we observe a universe with properties suitable for life simply because we exist in a cosmic region where life is possible. These theoretical explorations reveal that our observable universe, with its 2 trillion galaxies and countless stars and planets, might represent just one region within a vastly larger cosmic reality. The boundaries of direct observation may mark not the limits of existence, but rather the beginning of territories that extend far beyond our current ability to explore or understand. The mathematical models describing these possibilities continue evolving as scientists develop new frameworks for understanding cosmic reality beyond observational limits. Advanced computational methods allow researchers to explore the implications of different theoretical scenarios, testing how various models predict the behavior of cosmic regions that remain forever hidden from direct study. Current research focuses on identifying potential signatures that might provide indirect evidence for these theoretical frontiers. Scientists examine cosmic microwave background patterns, gravitational wave data, and large-scale structure measurements for subtle indicators that could reveal information about cosmic reality beyond our observational horizon. These investigations represent some of the most challenging work in theoretical physics, requiring sophisticated mathematical tools and computational resources. The exploration of these theoretical frontiers represents humanity's attempt to understand the full scope of cosmic reality using the tools of mathematics, physics, and scientific reasoning. While direct observation remains impossible for regions beyond our cosmic horizon, theoretical physics provides frameworks for investigating what might exist in these hidden territories and how they might relate to the universe we can observe. These investigations into cosmic reality beyond observation demonstrate how scientific inquiry pushes against the boundaries of the knowable, using theoretical frameworks to explore territories that may forever remain beyond direct study. The work reveals both the power and limitations of human understanding when confronted with the ultimate questions about the nature and extent of cosmic reality.